Hello, welcome back to algebra. Here we're going to be talking about graphing rational functions. So we've taken quite a journey so far. We've talked about what is a rational function, how to simplify them. Then we talked about the domain and the zeros of a rational function in the last couple of lessons. We also did a couple of sketches just to show you what the domain looks like, we talked about vertical asymptotes, the dotted lines, right? And then we talked about where the function crosses the x-axis. We called those the zeros of the, of the rational function. Now we're going to get a little more rigorous. We're going to actually graph these guys. And what we're going to do is I'm going to give you a rational function. And we're going to identify, first of all, where are the zeros, because that's going to be the crossing points of the x-axis of the function. Then we're going to identify the vertical asymptotes, where the function blows up to infinity because the denominator goes to 0. And then we're going to talk about something called a horizontal asymptote, which I'll explain as we get there, but basically that's where the function goes and has a horizontal dotted line that it approaches there. So we have vertical and horizontal asymptotes. We'll talk about that as we go along. And then we're going to create a table of values for these questions, and we're going to basically plot it by picking points, because I want you to get a really good understanding for what's happening on either side of all of these little dotted lines we have. You know, back in the day when we were learning about basic lines, equations of lines and graphing them, it was very simple. Just create a little table and there you go. And you plot it. But the problem with these rational functions is there's all these special landmines all over the place. I call them landmines. It's just points where the function either blows up to infinity or negative infinity, or that goes to 0 or something like that. And so we have to first find the special points, then we create a table of values to fill in the blanks and see what the function looks like. All right, so let's take our very first one, which will be very, very simple. It's the rational function that you're going to get very comfortable with as time goes on. F of x is 1 over x. How do we know it's a rational function? Because it's a function that can be written as a fraction, something on the top, something on the bottom. The something on the top happens to be very simple. It's just a number. And the something on the bottom also happens to be very simple. It's just the variable x. So it's quite simple compared to some of the other ones we've been looking at. But actually, this is one of the most important rational functions there is. This one is called a hyperbola. Hyperbola. So we're going to study hyperbolas quite a bit as we move on in algebra. So now you know about lines, mx plus b, right? That's a straight line. Then we learned about quadratics, or parabolas we called them, x squared, any kind of polynomial with x squared in there. Now we're learning about another very important kind of function called a hyperbola, and that is where you have an x on the bottom like this. 1 over x is the simplest kind of hyperbola. All right, so in order to graph this, we could just create a table of values, but before we do that, we need to go ahead and find what these special points are. So let's figure out, right out of the gate, where are the zeros of this function here? Where are the zeros? Well, we take the numerator and set it equal to 0. 1 equals 0. Now that looks crazy. 1 is not equal to 0. There's no variable at all in the numerator, so there's no possible values of x that could drive it to 0. And you can tell right away by taking your numerator and setting it equal to 0 that this is impossible. So what this means is there are no zeros of this function f of x. In other words, this function never crosses the x-axis, and we're going to see it as we graph it. It does not cross the x-axis. There are no values here where the function goes to 0 or crosses or goes and touches the x-axis. And we can see that by just doing this very simple thing. Next thing we're going to do is we're going to try to figure out what the vertical asymptote is. Vertical asymptote. Now, vertical asymptote, remember in the last lesson we talked about, comes about by taking the denominator and setting it equal to 0. And we said that that restricts the domain. The domain cannot include values where the denominator goes to 0 because it blows up to infinity. And we graphed it, I kind of sketched a couple showing you the dotted lines, the vertical dotted lines. The function can never get to that dotted line. It's like the light barrier, the speed of light. Nothing can go faster than that. So the function, if there is a vertical asymptote, will never cross that line because it'll just get closer and closer and closer without ever getting there. So how do we find these vertical asymptotes? We just take the denominator and we set it equal to 0. Now in this case, it was very simple. Once we take the denominator and set it equal to 0, there's nothing left to do. The value of the vertical asymptote is the vertical line x is equal to 0, or the points on the axis where x is equal to 0. So in our coordinate grid, when we draw this, if we put a dotted line right on top of the kind of the y-axis there, that's the vertical line x is equal to 0, the function will never cross that point. It'll just go to infinity at that point. Why? Because when we put 0 in here, the whole thing goes to infinity. It's undefined there. So if I asked you, what is the domain of this hyperbola? You would say all real numbers except when x is equal to 0. That's the only number not allowed. Every other number is fine. Okay? Now the next thing I want to do is I want to ask you, and this will be a lot more clear when we actually graph the thing, which we're going to graph in just a minute. But since we're doing all the special points early, let's talk about the concept of horizontal asymptote. Now, we haven't actually talked about this much, but we talked about vertical asymptote, and you know that that's where the graph gets very, very close to that vertical dotted line, but never gets there. The horizontal asymptote is the same kind of thing. It's a dotted line, but a horizontal dotted line where the graph never crosses it in the horizontal direction. And the way you figure out what it is you don't set something equal to 0, but you just do a thought experiment. You say, what will happen if I take x and I let it go to infinity? In other words, what happens if I let x go to 100? That's not infinity, but it's big. Then the value goes to 1 as 1 over 100. That's a small number. As x gets even bigger than that, like 1,000, then it's 1 over 1,000. If x goes to 1,000,000, then it's 1 over 1,000,000. If x goes to 10 million, see, we're trying to get as close as we can to infinity, but infinity is not a number. You never really get to infinity. But if you let x get bigger and bigger and bigger and bigger and bigger and bigger, then you see, what does the function do? And as x gets bigger and bigger, let's say x is 10 million, so 1 over 10 million. What if x is 10 trillion, 1 over 10 trillion? Well, 1 over 10 trillion is an incredibly small number, 1 divided by 10 trillion. We can let x get even bigger. What about x going to 10 quadrillion, or 10, even 10 quadrillion times quadrillion, something really, really huge? The denominator gets bigger and bigger and bigger. The entire fraction gets smaller and smaller and smaller. So what we say is that as x actually gets bigger and closer to infinity, what it means is that f of x approaches 0. It gets closer and closer to 0, because as x gets bigger and bigger and bigger, this fraction gets smaller and smaller and smaller, and the limiting process, we talk about limits a lot later when you take a calculus class, but as x gets bigger, 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 f of x gets closer and closer to 0. So what this means is, and it's going to be a lot more clear once I get the graph on the board, what it means is that the function, as we go farther and farther in the horizontal direction, gets closer and closer to the value of f of x equaling 0. So it helps us graph the function, because we really want to know what happens when x gets big this direction, what happens when x gets big the other direction. All right, now the next thing we need to do to make progress is actually go ahead and make a table. So we know the function will not cross the x-axis. We know we have a vertical asymptote. We know we have a horizontal asymptote, even though I haven't even shown you what that really means. So in order to make progress, let's go ahead and make a full-blown table of this guy. Let's pick values of x, and then we'll plug it into corresponding values of f of x, which is just 1 over x. So we're going to pick some representative values. What values do we pick? It's really up to you. I'm just going to pick a few, and that way we know we have some ideas, but I mean, I really don't know exactly what to pick ahead of time unless you have experience. But I do know I'm going to have a vertical asymptote right in the middle of the graph. So let me pick some points to the left and to the right. So let me pick x is -2, x is -1. Just to make it fun, let's make x is equal to -1/2. Then we get to 0. Then we get to +1/2. Then we get to +1. Then we get to +2. Why did I pick these numbers? Well, these aren't special. I could pick different numbers. I could pick -3. I could pick -1.5. I could pick -3/4. But I'm trying to pick numbers that are going to be relatively easy to calculate. Something that's not going to need a calculator. Because all I need is a few points and I can graph this whole thing. So what do I do with -2? I say, well, over here, I'm going to plug it in here. So I'm going to have 1 over -2, which is -1/2, but I'm going to write it as a decimal, which is going to allow me to plot it a little bit easier, -0.5. -1, I'm going to stick it in here. It'll be 1 over -1. When you divide that, you're just going to get -1. When you stick the -1/2 here, you got to be careful. It's 1 over -1/2. And when you take this and you divide it, what you do is you change it to multiplication. So what you're going to get is actually -2. Think about it. If you take the sign away, what is 1 divided by 1/2? It can go 2 times, right? So it's going to give you 2, but then there's a negative sign there. And if you want to think of it in terms of fractions, you take the denominator fraction, flip it over, multiply, and you get the -2. Now what happens here? 1 over, taking the 0 and putting it in, 0. Well, I can't divide by 0. So you can write infinity if you want here, but I'm going to write undefined. the truth is, as you get closer and closer to 0, it gets bigger and bigger and bigger. You see what's happening on the negative side, it's getting bigger and bigger and bigger and bigger, but as I get closer, I'm going to get all the way to negative infinity, and then what's going to happen on the other side? Plugging this in, I'm going to have 1 over 1/2. It'll be exactly what I have here, except it'll be a positive 2. I stick a 1 in there, it'll be 1 over 1, which is going to be a positive 1. I stick a 2 in here, it'll be 1/2, which I know is 0.5. So you see, this is nice and symmetrical. This is why this is such an important function, because it's very symmetrical. I have negative 0.5, negative 1, negative 2, undefined, basically infinity, and then I have 2, 1.5. Everything is symmetrical, negatives here, positives here, but the numbers are the same. So let's go ahead and attempt to graph this thing. Now, are we going to make it an amazing, high-quality graph? No. The point isn't to be a computer. The point is to understand what the function is doing. So I'm going to have x, and I have f of x. Now, what do we know from this? We know that the graph will never, ever cross the x-axis. We think, or we say, that we have a vertical asymptote here, there at, well, you know what? Let me do the asymptotes later. Let's plot the points. So I have negative 2 to positive 2. So let's go, here's negative 2, negative 1. Here's negative 1. You know what? Let me actually make it even bigger. Let's do it like this, just to give me a little more room. Let's do it like this. Let's do this at negative 1, this be negative 2, this is of course 0, this is of course 1, and this is of course 2, because I have negative 2 going up to 2 here. Now, what values do I have over here, right? Let's take a look and see what I have. I'm going to have a negative 2, I'm going to have a 0.5, and so on. So let's just take the same scale. Let's make this 1. Let me think about how I want to label this thing. Let's make this a 2. We'll make this negative 1. We'll make this negative 2, like this. Now, where do my points fall? Negative 2, comma, negative 0.5. So negative 2, and of course I messed up already. This is in the way. So we'll put this negative 2 here. So negative 2, negative 0.5 means there's a point right here. Okay? Negative 1, comma, negative 1 means there's a point right here at the intersection of negative 1 and negative 1x and negative 1y, like this. Then I have negative 1/2, which means x is right here in the middle, and I go all the way down to negative 2, which means I drop really far down here. All right? Then what happens? When I get all the way to 0, it's undefined, but that basically means infinity. But you can see what's going on here is that the graph, if I were to connect the dots, is bending over and actually coming down and getting really, really close, but never quite reaching that axis. I know I kind of drew it like it goes through there, but it actually doesn't. It kind of bends over and kind of just gets very, very close without actually getting there. Now let's plot the points on the other side. 1/2, comma 2. 1/2, comma 2 means a point right here. 1, comma 1 means a point right here. And 2, comma 0.5 means there's a point right here. Same kind of thing. The graph gets very, very close to the axis there, but not quite. Then it bends over, then it gets very, very close like this. This is what this rational function looks like. You might as well memorize it. It's called a hyperbola. It's one of the most important functions in algebra. Just like line is important, just like a parabola is important, you know, the smiley face graph, hyperbolas are equally important. We're going to talk about hyperbolas a lot more later on as well. But you can see what's going on. Let's make sure it makes sense with everything we learned. The function does not cross the x-axis. There is no value where the function is 0. Well, look, what we're saying is if you continue this table back to negative infinity or back to positive infinity, the line never gets to the axis. So there is no crossing point. You see, it gets really close. It gets really close. But if you were to take these numbers and really graph it on to the negative infinity and positive infinity, you would never cross this axis. So there are no zeros of this function. We're saying there's a vertical asymptote at x is equal to 0. So now we can see it very clearly, and I can now put my little asymptote dotted line here, which is a little cumbersome. It should be right on top of this, but I'm trying not to obscure it. There's a vertical asymptote here, right on top of the y-axis here, that the graph never approaches. It's like a speed of light barrier. It can never punch through it. The graph gets very, very infinitely close to it, but never goes through it. All right? Same thing on this side. There is a vertical asymptote there. And then we did a thought experiment. We said horizontal asymptote. What happens as the function gets when the value of x gets very, very big? What happens to the function? We said, well, when the value of x gets big, this fraction goes to 0, or very, very infinitely close to 0. And that's what's happening. As the value of x gets bigger, 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 1 over 100, 1 over 1,000, 1 over 10 million, 1 over 20 million, this graph gets infinitely close. And so we then say that this is now something special as well. So we put a little dotted line here, which is hard because it's right on top of the axis, but this is called a horizontal asymptote. So this green line is called a horizontal asymptote. And the equation of this green dotted line is a horizontal line at y is equal to 0, right? Y is equal to 0 is a horizontal line. And then we say that this purple graph, we call this a vertical asymptote. And we say that that's a vertical line. Remember, vertical lines look like x is equal to something. In this case, x is equal to 0. Vertical line, horizontal line. So the vertical asymptote is x is equal to 0. The graph never crosses that. The horizontal asymptote is also, or is very similar. Y is equal to 0. The green line, the graph never crosses that. So when we graph these rational functions, it's important to figure out what the vertical asymptote is, also to figure out what the horizontal asymptote is. Then we pick a few points on either side of all these dotted lines to figure out what the function really and truly actually looks like. So if you were to continue your table out to -3, -4, -5, -10, -100, all that's going to happen is you're going to get closer and closer to 0, but in the negative sense. Because if you put -1,000 in here, it'll be 1 over -1,000, which means that's very small. Negative number very close to 0, which means it's going to bend over negatively, but very close to 0. If you put bigger, bigger numbers onto positive infinity, like 1 over 10 million, you'll have a positive number very close to 0 here. And then around 0 here, the actual value of 0 is completely forbidden, right? But on either side of 0, we go to negative infinity and positive infinity because on this side of 0, very close on the right, 0.00001, 1 over 0.00001, if I put it in the table, will give me a very big positive number. And over on this side, it would be negative 0.00001. If I put that in 1 over negative 0.00001, it would be a very big negative value. So you can put extra values here all you want, but the point is not to graph like a computer. The point is to graph like a human being, to understand what the graph is saying. So what we do is we find what are the zeros. In this case, there were no zeros. What are the vertical asymptotes? We figure that by setting the bottom equal to 0. Then we figure out what the horizontal asymptotes. We say what happens to the function as we get bigger and bigger to positive and negative infinity for x. Okay? Then we plot some actual points, put them on the graph and connect the dots, and then we see the pink line is what this function looks like. So of course, you could stick it in a graphing calculator and get the answer. But now you can see why these equations are special. They have very special asymptotes, they have very special crossing points, and so on. So what we want to do next is plot another rational function, of course. And the next rational function is going to be f of x is equal to x plus 1 over x minus 1. X plus 1 over x minus 1. How do we know it's a rational function? Well, because it's a function that can be written as a fraction. Numerator divided by denominator. That's all it means to be a rational function. All right, so then we want to do the same kind of thing. We want to split it up into 3 parts. Zeros, vertical asymptote, horizontal asymptote. Let's see if we can kind of figure out what it might look like before actually doing the plot or doing the graph. So what are the zeros of this function? To figure out what that is, we just say the numerator x plus 1, we set it equal to 0, which means there is a 0 at x is equal to negative 1. There is a crossing point at x is equal to negative 1 where the graph cuts through the x-axis, okay? Then we say, what are the vertical asymptotes? For that, we take the denominator, x minus 1, and we set it equal to 0. Move it over, and we say that x is equal to 1. So at the value x is equal to 1, there's a vertical dotted line that the graph can never, ever cross. If it gets close to it, it just goes to either plus or minus infinity, and we'll see that as we graph it. But it's like a light barrier there that you can't cross. And then for the horizontal asymptote, we have to do a little thought experiment. We say, what happens as x goes to positive infinity? What happens to this thing? What does the function behave to be? Well, you can think of this a number of ways, right? It's x plus 1, x minus 1, numerator and denominator. So you got to think of a really, really big number. What you're thinking of, let's take 100, right? If x is 100, it's going to be 100 plus 1, and it's going to be 100 minus 1, which is what? It's 101 over 99, right? So that's what it would be if x were 100. But if x were like a million, then you would have 1, 0, 0, 0, 0, 0, 0, plus 1 over 1 million minus 1. So you're going to have 1,000,001 divided 1,000,000 minus 1. Now you see what's going on here is if I let x get bigger and bigger, if I let x get to 10 bajillion, that's not even a word, okay? 10 quadrillion, that's a word. That's a really big number. 10 quadrillion plus 1 divided by 10 quadrillion minus 1. For all practical purposes, the numerator and the denominator, when this gets really big, are basically going to be the same number. Yes, of course, they're going to just differ by just 1. The numerator is bigger than the denominator by 1. But as x gets bigger and bigger and bigger and bigger and bigger, the numerator is going to basically be exactly equal to the denominator. It's going to be so incredibly close that when you divide those numbers, you're basically going to get an approximate value of 1. As this gets bigger and bigger, you're going to get very, very, very close to 1. 1.0000001. And as you let x go to infinity, it'll be very, 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 very close to approaching the value of 1. So that means that this function, as x approaches infinity, f of x approaches the number 1. See, this one approached 0. Well, that was because the function was different. But as x gets bigger and bigger, there's a horizontal dotted line, but not at 0. There's a horizontal dotted line where y is equal to 1, where the function slides down like a water slide, and it can never quite cross that, but it gets very, very close. Because as you get larger and larger, you approach 1. And by the way, this whole approaching stuff, you're basically doing basic calculus. I mean, you don't really know it yet, but when you learn calculus, the first thing you do is learn about these things. We call them limits in calculus. So we're not talking about limit theory here, but this is essentially what you do to figure out what the horizontal asymptote is. So the next thing I want to do is create a table. This table, we're going to do a little bit better job. We're not going to do an extensive table for every one of these problems, but we'll do it for this one. So we have x and we have f of x. X plus 1, x minus 1. And we're going to create a table of values. What values do I put in my table? Well, you know, you do a little bit of guessing after a while. Let's go ahead and and you kind of get some experience. But the bottom line is I know there's a vertical asymptote at 1, so I want some points on the left and some points on the right of there. So I'm going to go -3, -2, -1, 0, 1, 2, 3, and I'm going to go out one more to the number 4, and you'll see why in just a second. The bottom line is this is a special point at 1, so if this is the middle, right, then I want 1, 2, 3, there's 4 points here, and 1, 2, 3 on the right is good enough to go ahead and get an idea. I could go one more point out if I want, but it's not going to really help too much. All right, so now I want to take this and I want to do the calculation. So what do I have? I plug this in. On the top, I'll have -3 plus 1 over -3 minus 1. So what I'll have is -2 over -4. Let me double check myself, -2 over -4. So I'll get, when I simplify this, 1/2. Positive 1/2 because the negatives cancel. When I put the -2 in here, I'll get -2 plus 1 over -2 minus 1. So on the top, I'll get a -1. On the bottom, I'll get a -3. And again, -1 over -3 is going to give me positive 1/3. So I have to write them and leave them as fractions. Then what's going to happen at -1? What's going to happen at -1? I'll have -1 plus 1 over -1 minus 1. On the top, what's going to happen is I'm going to have a 0. Notice I said there was a 0 at x is equal to -1. So on the top, I'll have 0. On the bottom, I'll have -2, which means that's my 0 point that I already found from before. Now let me switch colors to break up the chart a little bit. When I put the value of 0 in, what happens? 0 goes in here. I'll have 0 plus 1 over 0 minus 1. I'll have 1 over minus 1, right? 1 over minus 1, when you do that division, you just get -1. Now what happens when I put a value of 1 in here? Put the value of 1 in, I'll get 1 plus 1 over. Put a 1 here, I'll get 1 minus 1. That's a problem. 2 over 0. I can't do that. It's undefined. I already figured that out, actually, because the vertical asymptote is set the denominator equal to 0. I knew there was going to be a problem here. And this is shown in my table because I get an undefined value there. Now when I put the value of 2 in, I'll get 2 plus 1 over 2 minus 1. So I'll get 3 over 1, which is 3. Let me speed up a little bit. I'll have 3 plus 1 over 3 minus 1. It'll be 4 over 2, which is 2. Let me just double check myself. And then 4, I'll have 4 plus 1 over 4 minus 1. I'll have 5 over 4 minus 1 is 3. So 5/3. And if you put that in a calculator, it's going to be easier to graph it as 1.666 and repeating decimal like this. Let's just kind of pop that off here. Let's call it 1.66. So I've created a table. I know I have a vertical asymptote. I know I have a horizontal asymptote. I know the graph is going to cross the x-axis here at x is equal to -1. And now I've created a table to go ahead and try to graph it. Again, we don't want to graph it like a computer. We're not going to pick 35 points, but we have enough on either side of all of our dotted lines to figure out what this thing is going to look like. So let's go ahead and draw. This is the f of x value, the graph side of the graph. So we have x, we have f of x. All right. Now I need to go ahead and draw my numbers. So I have -1, -2, -3, +1, +2, +3, and I went to +4. Notice I took my values from -3 all the way to +4. So what I'm going to have here is -3, -2, -1. This is 0, and I'll just do this as 1, 2, 3, 4. Now I have to figure out what to do up here. Now I went as high as, here's 1/2, here's 1/3, here's 3, and so on. So I don't really need to go too big here. So let's go ahead and do it as, here's 1, 2, 3. We'll go ahead and put this as 3. And this is -1, -2, -3. We'll put -3 down here. We're not really going to need that. All right, and then let's go ahead and draw our vertical and horizontal asymptotes. We're saying, first of all, that the graph crosses the x-axis here at -1. So we're claiming that it actually has a crossing point here, so I'm going to put a dot there. And then we're also claiming the graph has a vertical asymptote at x is equal to +1, which is right here. So let me go ahead and draw a vertical dotted line all the way down. The graph cannot cross this. It's going to go blow up to plus or minus infinity there. And then we're also saying that there's a horizontal asymptote at f of x is equal to 1. As the value of x gets very, very large, the graph only goes infinitely close to the value of +1. So we're going to draw a value straight through here like this, because this is y is equal to 1. And then this vertical dotted line here is going to be, we'll do it down here. This is x is equal to 1. So x is equal to 1 is a vertical line, y is equal to 1 is a horizontal line. Now let me pick a color to draw the actual graph, and let's see what it looks like. We have -3, 1/2. -3, 1/2 is here. Okay. Then I have -2, 1/3. So -2, 1/3, that has to be less than the 1/2, right? It's 1/3. So I'm going to call it something like this. Is it exact? No, it's not exact, but I'm going to go ahead and put it right there. And then we say, actually it's going to be a little bit higher than that. It's going to be a little bit higher than that, close to 1/2, but not quite like this. Then it goes through this point. We already said that here. -1, 0, we already have that point on there. This guy is at 0, -1. 0, -1 means there's a point right here. So it looks like it's kind of going through these points right here. And then what happens at at 1 is it's undefined. When it gets to 1, it's undefined. So what happens is the graph starts off close to this line, goes through these points. Let me see if I can cut through this. And then just gets infinitely close to the red dotted line, but never crosses it. Then what happens on the other side? We have 2, 3. 2, 3 starts way up here. Then we have 3, 2. 3, 2 is right here. And then we have 4, 1.66. 4, 1. Here's 1. 1.66 is something probably like this. And I could have picked another point and so on, but now you can see the pattern. It cannot cross this dotted line. So it comes down something like this. It goes through all 3 of these, and it never ever gets past this. You can put little arrows here if you want to kind of show that the graph continues on like this. This is how you graph a rational function. First thing you do, what are the zeros? Set the top equal to 0. Set the bottom equal to 0 for the vertical asymptote. For the horizontal asymptote, let the thing approach infinity and see what the function does. In this case, we can see that it approaches 1. But even if you don't do that, if you put enough points in here, you will figure out that this graph will never, ever, ever get actually to 1. It'll get infinitely close on both sides like this. You put your horizontal asymptote of y is equal to 1, your vertical asymptote will be found as x is equal to 1, and then the points are just there to kind of guide you. Once you have that, you know it can't cross the dotted line, so you have to be between those. You know it can't cross this dotted line or this green one, but it has to go through those points, so there's only really one way you can do it, and that's the way we've drawn it here. This is the fundamental essence of how you graph rational functions. Is it fun? Kind of. Is it tedious? Yes, because you have to figure out all these little things, and then you have to calculate all these points. But as you get better, you'll just be very quick at understanding what the vertical and horizontal asymptotes look like. That's going to govern where the graph has to live. Once you pick a few points on either side of these lines, then you know how the graph has to slope. So make sure you can do all of these yourself. Make sure you can solve them and graph them, then follow me on to the next lesson where we will continue graphing rational functions.